And we're back. Welcome back and happy Tuesday. Today, we will pivot our discussion focusing on another learning model, namely linear regression. Before we begin, some administrative bits. There are two pieces of information I'd like you to look at concerning regression. There's a PDF on the course Blackboard on ordinary least squared linear regression, which is what we're talking about. And there's also a video from point 21 minutes and 39 seconds in the video. This URL will bring you to the right place. Please make sure you are looking over this as part of your study for the material. Okay, so why don't we get started? So we talked during the semester about the so-called anatomy of a learner. And for this, we outlined and highlighted the red boxes, those components in the anatomy of a learner over which you do not have control, and these black components, those over which you do have control. And focusing on the things you do have control of, we called the combination of the hypothesis set, our candidate formulas, and the learning algorithm, that mechanized process that searches for working hypotheses that most closely mimic the labeling action of the unknown target function. The combination of our learning algorithm and hypothesis set is called our learning model. Now, of course, we're searching through the action of our learning algorithm through our hypothesis set for that working hypothesis that mimics the labeling of the target function. Now, of course, how we measure that coincidence is using our so-called pointwise error E of x. Now, you search, and compare on for some number of rounds until you arrive upon a final best hypothesis that we're calling G. And so we talked about the credit approval problem, where you input vector-valued quantities describing collectively a customer, and these vector-valued quantities have associated with them labels +1 for positive examples, those who were approved for a loan, and -1, the so-called negative examples, those who were denied a loan. And so, therefore, our target function for each one of our customer records from the historical database of the financial institution, we have an associated ground truth label, and our learning algorithm is trying to find a function that most closely matches or mimics this labeling of the target function. And so we talked about this credit approval problem, and we have our linear model set of weights in D dimensions, where the dimensionality is the number of attributes culled from the credit application, and collectively the D many attributes describe a single customer. Now, these things might be factors such as the number of years in residence, the annual salary, the amount of outstanding debt, and so forth. And for each one of these attributes collectively describing our customer record or customer vector, we have a corresponding weight for our linear function. And so these weights, therefore, are W1 up to including WD. And so for our D-dimensional customer feature vector, we have a corresponding D-dimensional linear function. Now, of course, in 2 dimensions, that's a line on the plane. In 3 dimensions, that's a plane or flat sheet in 3 dimensions in R3. And then in more than 3 dimensions, we have what we call a hyperplane. So a hyperplane is just a generalization in higher dimensionality of this linear model. And so we have an associated threshold, and that threshold was the litmus test to determine from our weighted combination, X1, W1, up to and including XD, WD. We add those factors together, those weighted sums, and we get a score. And this threshold is compared against the score, and we approve that particular customer described by his or her vector for credit if their score exceeds the threshold, and we deny if it does not exceed the threshold, if it's less than the threshold. And so in this, we have what's called the binary decision problem. We have either a yes, no, +1, -1 answer. Now, in this case, imagine then if instead of saying you are approved, yes or no, a binary output for the labeling action of the unknown target function that we're trying to mimic through search through the space of hypotheses, imagine instead if our label were real value. Now, if our label were real valued, it'd be a scalar, like 27.3, and the scalar then is going to represent not whether or not someone is approved for credit, but the amount of their credit line. And so whenever you have a prediction problem and that label is real value, we call that a regression problem. And so with this, we're going to take our credit approval problem and change it into a regression problem. And so what we're trying to predict then is associated with each customer record, not whether or not he or she is approved for credit, but we're trying to predict the amount of credit that they would be extended or have been extended from the financial institution. Now, of course, if someone is denied credit, the line of credit is going to be $0. And so we still have a solution for those examples that are the negative examples if we're treating things as a regression problem and therefore trying to match the assignment of real values, scalars, to each one of the historical records. We're trying to mimic that assignment of labels, real valued labels, by unknown target function. And so how are we going to do this? Well, we're going to need a few more tools, and we're going to use the tools of linear algebra. Yes, seriously, linear algebra. Now, of course, you all have taken algebra way back when, and in algebra, you deal with scalars and variables. And these variables take on scalar values. Now, of course, you learn operations like equations and additions and subtractions and the procedures you can follow in order to solve for these unknown variables to get scalar values for them that respect the rules of mathematics. So in linear algebra, the prime focus is on the variable and the scalar, and operations on those variables and scalars. In linear algebra, our focus is a little different. The primary focus is the matrix. Now, of course, it's not that matrix, the best movie ever, starring Keanu Reeves. It's the other kind of matrix. Now, the best linear algebra course at DSU is Dawn Lott, Professor Dawn Lott, and I encourage you to take linear algebra with her. She does a fantastic job. But if you're out there studying on your own, the best linear algebra course in the world, I would say, is by Gilbert Strang, and there are course videos available on MIT OpenCourseWare. I really highly encourage you to go look at this if you want to learn linear algebra. It does a great job in boiling down this system of operations on matrices and functions on matrices in a way that is very, very simple, in a beautiful way. Just because it's linear algebra, it doesn't mean it has to be difficult. And Gil Strang does a wonderful job in doing that. So what exactly is the matrix? Not the movie. Let's talk about matrices in linear algebra. The primary focus in this new algebra system of operations and procedures on this other type of thing. So a matrix, the other matrix, not the movie, is a two-dimensional array of numbers. Now here we have a two-dimensional array, and if you look at it, you can measure the size of this two-dimensional array. It has 3 rows, and it has 4 columns. And so we would call this a notional 3x2 matrix. When you read off the measurements or the dimensionality or rank, as it's called, of a matrix, you first call out the number of rows, and then you call out the number of columns. So we'd say this particular matrix is a 3x2 matrix. Now, of course, in linear algebra, the focus is matrices, but there's something beyond a 2x2 or a two-dimensional matrix. It's called a tensor. If you have higher order dimensions, not just two-dimensional. We have one measurement in the number of rows, one in the number of columns, but you could go to 3 dimensions, 4 dimensions, and beyond. Now, of course, when you go beyond 2 dimensions, that has a name. The generalization of a matrix is a so-called tensor. And of course, if you're dealing with tensors, it no longer is called linear algebra. It's called tensor algebra. And so a matrix is nothing more than a so-called 2D or two-dimensional tensor. And of course, in tensor algebra, you have tensor products, tensor quotients, you can do multiplication, division, addition, all sorts of operations. It's just a whole new set of algorithms and procedures associated with these higher order matrices that we call tensors. And if you deal with machine learning, a very popular framework for doing deep learning is something called TensorFlow. It's just a framework for doing tensor operations, higher order matrices, in a distributed system. All right, so going back to our two-dimensional array of numbers, our matrix, we have a set of operations for doing products, for doing division, for doing addition, subtraction, inversion, and so forth. And that's what you study when you look at a course, traditional undergraduate course, junior level course in linear algebra. Okay, so let's take this two-dimensional array of numbers, and what if we were to expand it into m rows arbitrarily and n columns? So no longer it's 2 by 3 or 2 by 4, it could be 100 by 70 or 75 by 23. And so we call that a so-called m by n matrix, where m is the number of rows for that two-dimensional array, and n is the number of columns for that two-dimensional array. So we have our two-dimensional array of numbers, and one of the things we are concerned about is whether or not this matrix is rectangular or whether it's a square matrix. A rectangular matrix is one such that the row count is not equal to the column count. Now remember, a rectangle is a shape where the length and the width are not equal to one another. Hence, we call it a rectangular matrix. It's almost like drawing a rectangle. Now, if we have the case where the number of rows, the row count, and the column count are equal to one another, that's a so-called square matrix. Just like a square, the measurement of the height and the width are the same. And so the reason why we care about whether or not a matrix is square or rectangular is that there are certain properties afforded to a square matrix, namely it can compute an inverse, which is not the case for the rectangular matrix. But we're not going to dive deeply into all of these operations. We'll talk about them, and I'll leave them up to you to just look up the recipes for how you do certain types of operations, but we'll just talk about them a little bit as we need them in order to get to the regression solution, which is what we're after for this module. So we have our square matrix, and remember back in algebra, you had system of linear equations. Maybe it was a word problem that said Billy is selling cookies and lemonade. The number of cookies is a certain amount, and the number of lemonade is twice something, and then the total number of glasses of lemonade and cookies he sold was 4. And then you said the amount of money, there's another equation involving the number of glasses of lemonade and the number of cookies, and not equal to some other amount. And so you ended up in algebra with system of equations, and in that particular case, you had two equations governing the sets of relationships between the number of glasses of lemonade and the number of cookies sold. And then you also have two unknowns, in that case, the number of glasses of lemonade and the number of cookies sold. So you gave those unknowns variable names, x and y, chosen arbitrarily, and then you set up these equations. We have equation 1, in this case, x plus 2y is equal to 4, and that involves the two unknowns, x and y. And you had another equation, equation 2, 3x minus 5y equals 1. And that also involved your two unknowns, x and y. So what did you do in algebra to solve this? Well, you tackled these equations one at a time, finding a substitution for x in terms of y, and then you substituted that result into the equation number 2, and then you solved for y, and you went back and solved for x. So let's try that out. So here, we're going to take equation 1, and we're going to subtract 2y from both sides of equality, and mathematically it says in order to maintain the semantics or behavior of equality, whatever you do to one side of equality, you have to do to the other side of equality. So if we're going to subtract 2y from the left-hand side in order to get rid of that plus 2y, we also want to subtract 2y from the other side of the equality, the right-hand side. So that gives us x is equal to 4 minus 2y. So now this form of equation 1 is mathematically correct. We have not damaged what equality means, but it gives us a definition for x in terms of y. It says everywhere you see x, replace it with 4 minus 2y. So now we're going to take that second equation, equation number 2, 3x plus 5y minus 5y is equal to 1, and we're going to substitute everywhere we see x, we're going to substitute 4 minus 2y, what we had from our valid mathematical transformation on equation 1. So let's go ahead and do that. So we have 3 times quantity, 4 minus 2y. we have that minus 5y is all equal to 1. So now one of the observations to make for this substituted version of equation 2 is after we make that substitution for x that we got from our manipulations on equation 1, the result of that substitution into equation 2 doesn't have any x's in it. It's only in terms of y. So what this means is that we can now solve for y. So we group our terms, and we have, right, we distribute that multiplied by 3 by the parenthesized to the parenthesized expression. We get 12 minus 6y minus 5y is equal to 1. So we combine our y's. So we have 12 minus 11y is equal to 1. And then we are going to do some subtraction. We have minus 12 on the left-hand side, subtract 12 from the left-hand side, subtract 12 from the right-hand side. So we get rid of that 12 on the left-hand side, and we have 1 minus 12 on the right-hand side. And so we're left with 11 is equal to 11y. Conversely, you could choose to add 11y to both sides of equality. So the 11y on the left-hand side goes away because something minus itself goes to 0. And then you subtract 1 from both sides of equality. The 1 on the right-hand side goes away, and we're left with 11 is equal to 11y. So now, if you divide both sides by 11, you get y is equal to 1. So now that we know that y is equal to 1, we can then substitute that y is equal to 1 that we got from that substitution for equation 2, and we plug that back into equation 1. So if y is equal to 1, well, our result then that we get is x plus 2 is equal to 4, because 2 times y is 2. And then we subtract 2 from both sides of equality. We get x is equal to 2. So now what this gives us is that for this system of equations, the two equations in two unknowns, x and y, we get y is equal to 1, and we get x is equal to 2. Now, of course, that's all fine and good when we have two equations in two unknowns, but what happens if we have m equations and n unknowns? So here's equation 1, equation 2, etc., up to and including equation m, and then our unknowns, and many of them, we have x, y, z, w, etc., and here is our nth unknown. So what do we do then? Of course, algebraically, if we were going to find an expression for one of them from equation 1, and substitute equation 2, and substitute, sometime next year, we might find a result. That's just way too inefficient, and it will take us just an impractically long time. So, that's rough. What are we going to do? So we need new tools in order to deal with this arbitrary case where we have m equations and n unknowns. So let's now deal with matrices, and that's what matrices are for. It's a new type of algebra that traffics in not just variables and scalars, but systems of equations, set of equations in some set of unknowns. So in this case, we take our original example where we had the two equations and two unknowns, and now we're going to take the scalars associated with each variable, and we're going to put them into a matrix. So here we have 1 times x, 2 times y, so we write 1 and 2 for the first row of the matrix. So each row is going to represent the scalars of an equation. And then the second equation, we had 3x minus 5y. So our scalar for x in the second equation is 3, and the scalar for y in the second equation is minus 5. So we write 3 and minus 5 in our 2D array. So this 2D array represents the scalars associated with the left-hand sides of our equations in our two unknowns. So now then we write a vector, and this vector is going to contain our unknowns. So we have unknown x, we have unknown y. Now, of course, we have specialized operations for what it means to multiply when you have a matrix. Now, of course, when you have a matrix, how I remember it, you imagine you're in a boat, and it's a rowboat, so you row across the river and down the stream. Now, of course, when you're doing multiplication, if you take the first row of our matrix and you go down this vector, a so-called column vector, for our unknowns x and y, you get 1 times x plus 2 times y. That's exactly this first equation for the left-hand side of equality. And then that first position in that vector after the equal sign, that's also a column vector, that's exactly this 4 here, which is the right-hand side of equality. Let's do the same thing with the second row. So we row across the river and down the stream. So we say 3 and minus 5, position to position, 3 times x plus minus 5 times y. That's 3x minus 5y is equal to 1. And so this rowing across the river down the stream is how you multiply matrices and vectors. Now, if you had a 2 by 2 matrix times a 2 by 2 matrix, well, 2 by 2 is 4 total entries. So you're going to row across the river, down the stream. That product is going to give you, for the resulting product, that upper left-hand corner. And then across the river, down the stream for the second column, that's going to be this result. And then across the river, down the stream, that's here. And then across the river, down the stream, that's here. And so the result is another 2 by 2 matrix. So those are the semantics or the procedures, the behaviors you follow when you multiply matrices. And a vector is a type of matrix. A vector, a column vector, is nothing more than a 2-row, 2 times 1 column matrix. Okay, so matrices gives us a way, and therefore a new algebra set of procedures and operations, so that we can solve systems like this more easily when we have m equations and n unknowns, instead of a large number of times doing a substitution, another substitution, another substitution. Okay, so let's take a look at our matrices, and we have our system of equations, 2 equations in 2 unknowns. We have x plus 2y equals 4, and 3x minus 5y is equal to 1. So we have our 2 by 2 matrix. We'll call that variable A. And so now we're going to represent these matrices as variables. And then our algebraic operations by the rules of linear algebra are going to be applied to these variable representations of this number of equations and unknowns. And so now we have our matrix A. We're going to call this our coefficient matrix. We have our matrix X, it's 1 by 2, and this is going to be our unknown, or our variable matrix. And then this B, that's going to be our result matrix, or it's just this set of scalars. It's going to be also 1 by 2. Now, if we take these equations now, we can rewrite this entire linear system as AX equals B, instead of m equations and n unknowns. I'm just demonstrating it with 2 equations, 2 unknowns, but this works equally well with m equations and n unknowns. So now that we have this AX equals B, we use the tools and procedures defined by linear algebra for how you do algebraic operations in equivalent of multiplication, division, inversion, and addition and subtraction for these new items, these matrices, where before in regular algebra, variable algebra, we talked about scalars and variables. So here our variables represent matrices, which are these 2D arrays, or sometimes a 1D array, which represents systems of things or sets of things. All right, so we have this AX equals B, and what we're going to do then, we're going to multiply on the left-hand side by A inverse. Of course, equality means that whatever you do to the left-hand side of the equation, you're also going to do to the right-hand side. Now, in linear algebra, when you multiply, there's a difference between multiplying on the left and multiplying on the right. And the reason for that has to do with the measurements, or the so-called rank, of the matrix. And so I'll leave that to you to look up, but at this juncture, let's left multiply both sides of equality by A inverse, which is the inverse, or the reciprocal, as it were, of matrix A. So we have A inverse times A, that's times X. On the left-hand side, we have A inverse times B on the right-hand side of equality. Now, of course, anytime you multiply something by its inverse, for example, the number 5 times its inverse is 1 over 5, that's equal to 1. Now, this 1 in regular algebra has a special synonym when we describe it. It's called multiplicative identity. And what that means is that number, like 5, with multiplicative identity, that's going to give you back the number itself. And so said differently, if we multiply 5 by its inverse, we get this thing that we're calling identity. For matrices, identity is a special type of matrix, and it's a matrix where all the diagonal elements are equal to 1. So here is identity for a 2 by 2 matrix, and it's noted as I. So we have 1 along the diagonal, and we have 0 for all of the off-diagonal elements. If we had 3 by 3 identity, that would be 1, 0, 0, 0, 1, 0, 0, 0, 1. Again, we have all the diagonal elements are 1, and all the off-diagonal elements are 0. And for any 2 by 2 matrix, if we multiply it by identity, you're going to get back that matrix. And you can actually show this yourself using that matrix multiplication procedure, rowing across the river, going down the stream. All right, so now if we have, going back to this equation, A inverse times A, that's equal to identity, because something times its inverse is identity. So we get identity times X is equal to A inverse times B. And so that means X times identity, all right, that's just X because of multiplicative identity. It applies also for matrices, even though the definition of identity is this identity matrix. We get X. X times identity is X. So this gives us our result. The unknown vector, X, is equal to the inverse of our coefficient matrix A inverse, times B, our constant matrix, our 4, 1 vector. Okay. So now, let's look up our procedure, and you can actually look up how you invert a matrix. And A is a square matrix, and its inversion, a square matrix, is always invertible. For rectangular matrices, if you try to invert them, you do what's called losing rank, and it doesn't always work. So you can look up matrix inversion. It's a well-known procedure, 1 over the determinant times the matrix of cofactors, and I'll leave that to you to look up. But after following this procedure for inversion of the A matrix, the result is negative 1 upon 11, some scalar, times this new coefficient matrix, minus 5, minus 2 is the first row, and minus 3, 1 is the second row. So this is our definition of our A inverse matrix. And if you actually multiply this by the original A, you would get the identity matrix, our 2 by 2 matrix, where the diagonal elements are all 1 and the off-diagonal elements are 0. So now, going back to our definition of what X is, we said A inverse times B. We know our B matrix is this 2 row, 1 column, or 1 vector, okay? So let's go ahead and set this up. So we have X is equal to A inverse, so there's our A inverse, and times B, there's our B. So let's go ahead and do this operation. Again, we're going to multiply this new coefficient matrix for A inverse, rowing across the river, down the stream, and we get minus 1 upon 11 times this 2 by 1 matrix or vector, minus 22 and minus 11. So when we multiply this scalar by a matrix, and when you do scalar multiplication by a matrix, you apply the scalar to each term in the matrix. That's the rules of linear algebra when you multiply by scalar. This row across the river, down the stream, that's if you multiply a matrix times a matrix. And of course, when you multiply a matrix times a matrix, the ranks have to line up. So this is 2 by 2. This vector is 2 by 1. If this vector were 1 by 2, you can't do that matrix operation. These dimensions that butt up against one another, they have to be the same in order to do that product. That's the rules of linear algebra. So now we take this minus 1 upon 11 scalar, multiply it by this 2 by 1 vector, each term, and we get this xy, our x vector, is equal to this new vector 2, 1. So what does this say? It says x is equal to 2, and it says y is equal to 1, which is the same result we got before using the longer way, using rules we learned from algebra. And so, that's much easier. It's not so rough. And so what linear algebra does, it changes the focus away from single variables and single scalars to equations or linear systems involving variables and scalars. at the level of abstraction, so that when you do these algebraic operations, whose rules are defined by the rules of linear algebra, you don't have to pay attention to all of these small moving parts. You're thinking at a higher level. And so it's not so rough. You get the same solution much more easily using these new procedures. Okay, so let's go into what the regression problem tells us. Now, we said the regression problem, you input your vector representing a customer, and this is information that you would call from the loan application, and it's a d-dimensional vector, and so we might represent our x vector as being from d-dimensional real-valued space. Each one of these attributes is a scalar of some sort, and they have different meanings depending on the information from the loan application. And we also have our corresponding d-dimensional weight vector. So we're going to take a linear sum, w1 times x1 plus w2 times x2 up to and including wd times xd, and we're going to add all those terms together. Now, of course, we're going to get a score, and that score is going to be dependent on the weight vectors that we input for our linear model, the weights for this weighted sum. And we want to choose some hypothesis such that the score that we compute from that particular hypothesis is going to match or mimic the ground truth labeling by the unknown target function. So effectively what we're trying to predict is some dollar amount, where that dollar is that scalar from the set of real numbers. And we're trying to match that credit line amount, that dollar amount, assigned by the unknown ground truth target function. And so our regression, what makes it a regression problem is this real valued output. And so we treat this not as whether someone is approved or denied credit. We treat it as, can you predict the amount of the credit line? How much credit are we going to extend to this person versus some other person described by his or her attribute vector in d dimensions? And so we have, like from the learning problem we've discussed for classification, we have our historical data from the institution, and it's going to be n many data points representing big N many customers from our historical records. And so we have customer 1, x1 in d dimensions, 2, 3, 4, etc., up to including n. And then each one is associated with a label yi, where each of these y values is a dollar amount, which is the size of the credit line. And so in this case, what linear regression is after is choosing some working hypothesis that best replicates the decision criteria, i.e. the assignment of real valued quantities to each one of these customers based on their d-dimensional descriptor. So here's an example in 2 dimensions, and let's imagine on the horizontal axis we only had a single scalar representing the customer description. Let's imagine this is the amount of outstanding loan, student loan that someone has, because that's going to impact the amount of credit the financial institution is going to extend to you. And on the horizontal axis, we have the output of the ground truth label, so that's the label, the ground truth target function, and that's the amount of credit line extended to that person from the historical data. And so we have 2 variables, our independent variable x, that's that descriptor of the customer from historical data, and the dependent variable, that is the label, a real value quantity, the size of the credit line. And so these are some customers. Let's imagine customer x1 has a certain amount of student loan debt, maybe $23,000, and maybe the credit amount extended to that person was a credit line of $14,000. Let's say for this other student, their student loan debt is bigger, $58,000, and the credit amount extended to that person, credit line, was $6,000. Now, of course, we have our set of historical data, and now we want to find our line on the plane, our linear model, that most closely mimics these labels, these real valued quantities on the vertical axis. And this is going to be our h of x. Now, of course, for a different weight vector instantiation, where w is equal to w1, w2, up to and including wd, we're going to get a different h. So for a different setting of w, maybe we get that line. For another setting of w, maybe we get that line. So now we want to choose that hypothesis, that working hypothesis, from all the different hypotheses we can draw instantiations of the weight vector that most closely mimics the ground truth labeling. And so here for this hypothesis, for this value, let's call that x1, the hypothesis says it should be that value, that's h of x1. Now, of course, that might be off relative to what the ground truth target function said the credit line should be, f of x1. But we're trying to find the best line that most closely mimics for all of the data, historical data, our in-sample data, that most closely mimics for all of it the ground truth labeling by the unknown target function. Okay, so let's talk about this idea of residuals, how we select that best working hypothesis. And so here, we want to know how well our h of x, our working hypothesis, which is w transpose x, that weighted sum in vector form, is just our w expressed as a row vector, w1 through wd, times x as a column vector, x1 through xd. Now, of course, again, as we talked about the rules of multiplication in linear algebra, if that's our boat and you're in the rowboat, there's your oar, you row across the river and down the stream. So here it's w1 x1, w2 x2, up to including plus wd xd. That's just w transpose times x. Transpose means we're taking our w vector and turning it from this d row, one column vector, we're turning it into a one row d column vector. We're shifting the rows, we're swapping the rows and columns. So here, w transpose x is how we output that weighted sum, and we want that weighted sum to equal the label, that real value assigned by the unknown target function. So here, we're going to measure, or a way to select the line that most closely mimics the unknown target function, and that best working hypothesis is that w vector instantiation that sits in the middle of the data. So this particular line sits in the middle of the data, but it makes mistakes. It's off a little bit for some or even many of these input data points as it pertains to the labeling by the unknown target function. So we see for this first input, that's our difference. For our second input, our hypothesis is off by this much. Next one is off by this much. The next one is off by a lot. But it kind of sits in the middle. And in the middle is really the best you can do because you can't be perfect for all of them. And so this difference between the score output by the working hypothesis, which is here, and the unknown target functions credit line, which is here, that's going to be this difference. It's h of x minus f of x. And that difference has a name. It's called a residual. It's what is left over, or what resides after you consider the two. And so here we have our residual, the difference between our working hypothesis, credit line, our score from the working hypothesis, and score associated, or the real value label output or assigned to that customer by the unknown target function. So that's our residual, the difference between our working hypothesis on the input and the ground truth unknown target function. Now in this particular case, we have a negative residual. We have our ground truth target function, f of x, is greater than h of x. If we said h of x minus f of x and f of x is greater, that's going to be a negative residual. If we look at that other input, that's a positive residual. F of x is less than h of x. So that difference, h of x minus f of x, is going to be positive. So we have positive residuals and we have negative residuals. Now in this case, to be in the middle, we don't really care about the positive and the negative. What we care is minimizing the magnitude of these residuals. So what we're going to do then is we're going to use the square of this residual because we care about small magnitudes and not whether it's positive or negative. And so this term has a name. It's called the squared error loss. It's the square of the residual, that difference between the output of the working hypothesis and the label ground truth assigned by the target function. So we square it, i.e. the squared error loss, because we care about the magnitude and not the direction. And so here is for one input feature, dimensionality d equals 1, where we have a single attribute describing the customer, for example, like the number amount of student loan debt outstanding. And then in this case, we have two features. So this axis, this x2 hat direction, that might be the amount of student loan. And maybe this x1 hat direction, that might be the number of years in residence. Now, given years in residence and amount of student loan, this z-axis, this direction, that vertical axis, that would represent the amount of the credit line. Now, in this particular case, our linear model is a plane. You can imagine a flat sheet of paper at some orientation and some height, and that orientation and height is described by the weight vector associated with our linear model. And so in 3 dimensions, it's a plane. 2 dimensions, it's a line. More than 3 dimensions, it's called a hyperplane. And so in this particular case, we have 2 features, and our linear model is a plane. In the example we gave to explain what residuals are in the squared error loss, we have 1 feature, and our linear model is a line. And so now what we do, when we try to select that linear model, that is this notional in the middle, we're going to average these residuals to compute something called in-sample error. And that's going to be our measurement of how far away or far off from the ground truth target function our linear model, our hypothesis h of x is. So we add up all of those squared error losses, our residuals. That's our pointwise error we alluded to before, e of x. And we're going to sum them up from the first input, second customer, third, up to including the big nth customer. And we're going to divide by n. So we have 1 upon n. Our summation, n goes from 1 to big N, of this pointwise error, i.e. the squared error loss, between the output of the current working hypothesis on that customer vector and the ground truth unknown label by that ground truth unknown target function. And we square it because we care about the magnitude and not the direction. And so this is our in-sample error. It's the difference between our working hypothesis, h of x, and it's specific to each h of x, our instantiation of a weight vector. It's the measurement of coincidence between our working hypothesis and the labeling action of the unknown target function. And so now what we want to do is select some w, some hypothesis, that's going to make in-sample error the smallest we can make it. Because if it's small, en, then we know that that particular working hypothesis very or most closely matches the action of the unknown target function. Okay, so that's all I had for today, and we will pick back up next time on Thursday, continuing with our regression model and algorithm. So with that, we'll end there, and as usual, please stay healthy, stay safe, and I'll see you all